Section 3.4 video lecture. I am once again Dr. Scott Spaniel. I am your instructor for this course, and today we're going to talk about measures of position and outliers. So we've been talking about some of the numerical statistical summaries we can do to talk about midpoint, the middle of your data, and dispersion of your data, and so now we're going to talk about some numbers that speak to location in your data. Okay, and so that's what we're going to look at. So you can go ahead and take out your note sheets that we've been looking at for Chapter 3, which once again can be found in the Blackboard course or on my math lab, depending on how your course is set up. And turn to page 21. So the first thing we're going to look at is how to figure out where a individual point is located in a data set. An individual data value is located within the larger data set. Specifically, how many standard deviations it falls from the mean. So the Z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. So this is how many standard deviations we are from the mean. It is obtained by subtracting the mean from the data value and dividing this result by the standard deviation. So we take, in a population, we take x minus mu and divide it by sigma. And if we're looking at a sample, we take x minus x bar and divide it by s. Okay? And that'll tell you how many standard deviations you are from the mean. So this is a great way to compare values from different data sets is one thing we can use this for. So for example, in 2007, Jake Peavy of the San Diego Padres had the lowest earned run average, ERA. It is the mean number of runs yielded per 9 innings pitched of any starting pitcher in the National League with an ERA of 2.54. Also in 2007, John Lackey of the Los Angeles Angels had the lowest ERA of any starting pitcher in the American League with an ERA of 3.01. In the National League, the mean ERA in 2007 was 4.119 and the standard deviation was 0.697. And in the American League, the mean ERA in 2007 was 4.017 and the standard deviation was 0.678. Which player had the better year relative to his peers, Peavy or Lackey? Okay, so what we want to do is we've got Peavy, we've got Lackey, we want to find their z-scores. So to find their z-scores, we subtract their data value. So that's their ERA. So for Jake Peavy, that's 2.54. And for John Lackey, that's 3.01. And from that, we subtract the mean. So for the National League, that was 4.119. And for the American League, that's 4.017. And then we divide those by the standard deviations for each league. So the standard deviation for the National League was 0.697. And for the American League, it was 0.678. Okay. So now what we can do is we can type that into ClassCalc. So one neat trick that I'm not sure I've mentioned yet when you're doing this, if you're ever doing a division like this with a fraction bar, the first thing you want to hit is the divide, and then I'll throw that in there, and then you can type in your data. So this would be 2.54 minus 4.119 over, and you can use the arrow keys to move around, 0.697. And there's our z-score for Peavy, so negative 2.265. And then for John Lackey, it's 3.01 minus 4.017. Oh, and see, I already screwed it up. So notice the problem, if I hit divide now, is it only divides the second number. So whenever you're doing one of these fraction bar problems, hit divide first, like that. It's nice when I can make a mistake to show you the error of my ways all at once. And then divide by 0.678. And we get a z-score for John Lackey of negative 1.485. Okay. So that means that Jake Peavy was negative 2.65 standard deviations below the mean, and John Lackey was negative 1.485 standard deviations below the mean. And in general, the person that had the better year is the one that falls farther from the mean. In this case, ERA you want to be low because you want to, as a pitcher, you want to give up as few runs as possible. So the smaller number would be the better, doing better relative to his peers. So in this case, the person who did better relative to his peers is Jake Peavy because he had a lower Z-score. So he was farther from the mean for his peers versus John Lackey was for his peers. Okay, so that's how you do a Z-score, how you calculate one and how you can compare them. Now we can also figure out data values when we know what the Z-score is. So, for example, here, a highly selected boarding school will only admit students who place at least 1.5 standard deviations above the mean on a standardized test that has a mean of 200 and a standard deviation of 26. What is the minimum score that an applicant must make on the test to be accepted? So we can set up our formula, Z equals X minus X bar over S. Now in this case, the value we're looking for is not the Z-score, but the test score. So the test score here is the data value, so that's X. Okay, so that's what we're looking for, is we're looking for that X value. So we want to plug in our other values and then solve for that X. So our other values are, we have 1.5 standard deviations. Well, standard deviations here is Z, right? Z is number of standard deviations. So that'll be 1.5. X minus the mean, which is 200, divided by the standard deviation, which is 26, right? So there's a difference here between standard deviations and the standard deviation. Standard deviations is our Z, and the standard deviation is our S value. Right now we would solve this for X. So to solve for X, we multiply both sides by 26, right? We got to use a little algebra here. Okay, so 1.5 times 26 is 39. And then we can add 200 to both sides. So we get 239 equals X. So in order to make it into this school, a student has to get at least 239 points on this test. Okay, so that's the idea of how Z-scores work. So what I'd like y'all to do is flip over to the next page and try these two problems. Okay, so pause the video and try these two problems. Okay, so now that you've had a chance to try these on your own, let's go ahead and run through these together. So this one's very similar to the one we just did with Jake Peavy and John Lackey. It says the highest batting average ever recorded in Major League Baseball was by Ted Williams in 1941 when he hit .406. That year, the mean and standard deviation for batting average were 0.2806 and 0.0328. In 2007, Maglio Ordonez was the American League batting champion with a batting average of 0.363. In 2007, the mean and standardized deviation for batting average were 0.2848 and 0.0273. Who had the better year relative to their peers? So we've got Williams and we've got Ordonez. So for Williams' Z-score, we've got his data value is 0.406. The mean is 0.2806. And the standard deviation is 0.0328. And for Maglio Ordonez, we've got a data value of 0.363 minus his mean, which is 0.22848, divided by the standard deviation of 0.0273. Okay, and then we can just plug those in our calculator to see who had the best year relative to their peers. So Ted Williams had a Z-score of 3.823. and Megalodonius had one of 0.82864. And once again, farthest from the mean is best. In this case, farthest from mean would be the largest number, and that should make sense in context because in context, a higher batting average is better. Okay, and if you're ever confused about which one would be better as you're going through the homework or anything like that, feel free to just Google it. You could just Google which is better, a high or a low batting average, and I'm pretty sure the answer will be pretty easy to find. Okay, so that's the idea. Then down here, a manufacturer of bolts has a quality control policy that requires it to destroy any bolts that are more than 2 standard deviations from the mean. The quality control engineer knows that the bolts coming off the assembly line have a mean of 8 centimeters with a standard deviation of 0.05 centimeters. What lengths will a bolt will be destroyed? Okay, so same idea here, except in this case, that are more than 2 standard deviations from the mean could be either direction. So we're going to look at 2 equals x minus 8 over 0.05, but we're also going to look at negative 2 equals x minus 8 over 0.05. And then solve both of these very similar. So multiply both sides by 0.05. So that gives us 0.1 equals x minus 8, and then add 8. So we get 8.1 equals x. So 8.1 or more would get destroyed. And over here we're going to solve this in roughly the same manner. 7.9. So anything greater than 8.1 or less than 7.9 would get destroyed. So that's the idea behind z-scores. And z-scores are something we're going to use quite a bit in the later chapters of this book because they are used for position and for standardizing things so that we are all talking about the same things. So we'll look more at that later in the course. Okay. Now the next ones are about how do we break up our data set into different size objects. So the first of these is called the percentile. So percentile denoted P sub k of a set of data is the value such that k% of the observations are less than or equal to that value. So for example, if over here, if this is my data, okay, here's my minimum, and if this is P sub 1, that means 1% of the data is less than P sub 1. And if we kept going, and let's say this is P sub 2, then another 1% is between those two. Because there are 2% of the data that is less than that, right? So it gets broken up into 2 parts. And if we kept going to P sub 3, then there would be 3% of the data less than P sub 3, which would be another 1% in there. And if we kept going with this up to the top, then if this is the maximum value, and here is my, there's 1% of the data in each one of these, right? Then this last percentile would be P sub 99, because there's 1% of the data to the right, so there must be 99% of the data to the left. And so the next one down would be P sub 98, and then P sub 97. Okay? And so the idea here is that there are 2 ways to interpret any percentile. It is either the percent of the data that is less than that, or it is 100% minus that percentile would be the amount of the data that is greater than that. Okay, so let's go ahead and give this a try with a few examples. So the 15 percentile of head circumference of males 3 months of age to 41 is 41 centimeters. So that means that 15% of all males 3 to 5 months of age have a head circumference of 41.0 centimeters or less. Okay, so 15% of the data is at that value or smaller. Also, or we could say 85% of all males 3 to 5 months of age have a head circumference of 41.0 centimeters or more. So 15% of the data is less than the 15th percentile, and then therefore 85% of the data has to be more than that. Okay? So let's just do one more together, and then we'll move on. So one of the things, well, I'll mention that in a second. So if we were doing the 90th percentile, it would be almost identical idea. So this one would be 90% of females 2 years of age have a waist circumference of 52.7 centimeters or less. Right? When I'm matching the percentage to the percentile, it's going to be or less, because that's what the percentile means. That data value has 90% of the data less than it. Or I can do 100% minus 90% to get 10% of females 2 years of age have a waist circumference of 52.7 centimeters or more. Okay. And that's really all we're going to do with percentiles, because for the most part for this course, all I really need you to be able to do is understand what they mean. Because in order for a percentile to be useful to us, you really have to have at least 100 data values. That way there's at least one thing in each percentile, but you really need to have a lot more than that. These are mostly useful for very large groups of data, like, for example, the set of all females of 2 years of age. That's a really big subset. So therefore, this makes more sense. So for us, all we really need to know for percentiles is not how to find them, but just how to understand what they mean. So that's all we're looking at here. So if you can understand those two, you've got all you need to know for percentiles in this class. What we're going to focus on is something that's similar to percentiles, but breaks it up into a much fewer number of groups. And those are called quartiles. And they're called quartiles because they break it up into four pieces. So quartiles divide the data into four, so 4 equals parts. So if I draw my quartiles, okay, what I've got is this breaks it up into 4 equal parts, which I didn't draw very equal, but each have 25% of the data in them. Okay. Now, the number that breaks the data in half is called the median, or we can also now call it quartile 2. Then the number that breaks the bottom half in half is quartile 1, and the value that breaks the top half in half is quartile 3. Okay. To go along with this is something called the interquartile range, or IQR. We talked about range in section 3.2. It's simply the smallest value minus the largest value minus the smallest value. So with the interquartile range, what we're asking is, well, how far apart are the boundaries for the range? So how far is it from Q1 to Q3? So we take Q3 minus Q1, and that'll tell us that. Now, we use the interquartile range for a very important thing, which is finding outliers. So extreme observations are called outliers. And we can use interquartile range and quartiles to define what outliers look like. So checking for outliers by using quartiles. So first of all, determine the first and third quartiles of the data. Then compute the interquartile range. Then determine the fences. Fences serve as cutoff points for determining outliers. So fences are just like fences on your house or on your yard. Or around a property. If you are inside the fence, then you are not an outlier. You do not lie outside the fence. If you're outside of the fences, then you are an outlier. So to find the fences, for the lower fence, you take Q1 minus 1.5 times the IQR. And for the upper fence, we take Q3 plus 1.5 times the IQR. Okay? And if a data value is less than the lower fence or greater than the upper fence, then it is considered an outlier. So anything outside the fences is an outlier. So let's go ahead and practice these ideas with an example where they've already found the quartiles, and then after that we'll practice finding the quartiles using technology. So a violent crime includes rape, robbery, assault, and homicide. The following is a summary of the violent crime rate, violent crimes per 100,000 population for all 50 states in the United States plus Washington, D.C. in 2005. Okay, so first of all, they gave us the three quartiles, and the first thing says provide an interpretation of these results. Well, that's the same thing as what we were doing with percentiles. So there are about 6 different ways we could interpret these, but let's just do 1 or 2 together. So let's talk about Q1. So for Q1, we could say that 25% of the data, in this case, the states, have a violent crime rate of 272.8 per 100,000 in the population or less. Okay, so that works exactly the same. We can also say that 75% of states have a violent crime rate of 272.8 per 100,000 or more in the population or more, right? We could flip it around. For quartile 2, we do the same thing but with 50% both directions, right? Because it's splitting it exactly in half. And for Q3, it would be 75% are less and 25% are more. Okay? Then it wants us to determine and interpret the interquartile range. Okay, so the IQR is just Q3, 529.7 minus Q1, which is 272.8. Which is 256.9. And the interpretation for that number is that 50%, the middle 50% of the data has a range of 256.9 violent crimes per 100,000 in the population. Then it asks us, the violent crime rate in Washington, D.C. in 2005 was 1459. Would this be an outlier? Okay. Well, one way to find the way to find the outliers is to find both the fences. So the lower fence is Q1, Q1 272.8 minus 1.5 times the interquartile range, 256.9, and the upper fence is Q3, 529.7 plus 1.5 times 256.9. Okay, and so we can calculate both of those. And anything inside of those fences is going to be an outlier. Anything outside those fences is not going to be an outlier. So that's negative 112.55. And this one is 915.05. So first of all, are there going to be any outliers on the low side? And the answer to that is no, because we got a negative number for the lower fence, and in this case, there's no way for your data value to be negative, because crime rates have to be 0 or higher. So there's going to be no outliers on this side. No outliers on the low side. And then the question is, well, is Washington, D.C. an outlier? And the answer to that part is yes, because 1459 is greater than the upper fence. So it's outside, therefore it's an outlier. It says, do you believe the distribution of violent crime rates is skewed or symmetric? Well, there's a few. The answer to that is skewed. And the answer, and right, and there's a couple different ways you can tell that. One, there's an upper outlier but not a lower outlier. So that suggests skewed to the upper side, which is to the right. And if you look, the quartiles are split so that there's more of a split on the right than there is on the left. So this is just over 100, and this one's closer to, these two are just a little bit over 100 apart, and these two are almost 150 apart. So this is a bigger range. So the right side of this is longer, therefore it is skewed to the right. Okay, so that's the idea. So go ahead and take a moment and try these other two here. This other problem on page 25. So pause the video and try this, and then when you hit play, we'll go through it together. Okay, so now that you've had a chance to try these, let's go ahead and talk about them. So these values are for amount of time spent on the homework for the semester of a college algebra class. So provide an interpretation of results. So we talked about this a little bit earlier, but there's a bunch of different ways you could interpret these numbers, and each one basically has two interpretations. But let's just do Q3 this time. So we can interpret that as 75% of college algebra students spent 72.5 hours on online homework for the semester. Or more. Okay, so they spent a minimum of that's 75%. Or we could flick it around so that it's 25%, and then it would be or less. Okay, then it says determine and interpret the interquartile range. So the IQR in this case would be 72.5 minus 42, which is 30.5. So suppose the student spent 2 hours doing homework for a section. Oh, except this shouldn't be hours. Sorry, I misread this problem. This is minutes on online homework per section. Sorry, I misread the problem. Okay. So suppose the student spends 2 hours doing homework for a section. Would this be an outlier? Okay. Well, to do that, we just need to find the lower fence and the upper fence. So the lower fence is 42 minus 1.5 times 30.5, and the upper fence is 72.5 plus 1.5 times 30.5. Okay, so once again for the lower fence, we got a negative number, so there aren't going to be any outliers down there. And for this, we get 118.25. So is 2 hours an outlier? Yes, because these are in minutes, and 2 hours equals 120 minutes, which is greater than the upper fence, so 2 hours is an outlier. And once again, similar to the last one, this would be skewed right, because there's an outlier on the right but not the left, and the difference between Q1 and Q2 is only 9.5, but the difference between Q2 and Q3 is 21. So that's a much bigger range on the right, and it has an outlier. So most likely this is skewed right. Okay, so then the last thing in this section is just, well, how could we find these quartiles by hand or with technology? So let's go ahead and we'll do this first one. I think I have this set up so we could do both of these by hand, let's go ahead and try this first one by hand, and then I'll show you how to do it with technology, and then we'll answer these questions. So the quartiles, remember, are each have 25% in them. So what you want to do to find the quartiles is you want to start by finding the median, and then find the median of the bottom and top half. So if I go back real quick to the picture I drew, notice the median, or Q2, breaks this whole thing in half, and then Q1 breaks the bottom part in half, and Q3 breaks the top part in half. So we just need to find the median 3 times. So this data is already in order, so we just need to count off to find our median. So we've got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10. So our median is between these two numbers. Okay, so that's 39.7 plus 4.00 divided by 2, which is 3.985 is our median. Okay, so that breaks the data in half right here. So we've got a bottom half of the data and a top. So to find Q1, I do the same thing, but just for the bottom half. So I go 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Okay, so then Q1 is going to be 2.78 plus 3.41 divided by 2. And then I can do the same thing on the top half to find Q3. So that's 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And so Q3 is going to be 5.22 plus 5.50 over 2. And so we can do those calculations. So Q1 is 3.095 and Q3 is 5.36. Okay. And now we can compute and interpret the interquartile range. So that would be 5.36, this is the IQR, 5.36 minus 3.095, which equals 2.265. And remember, the interpretation of the interquartile range is it's the range of the middle 50% of the data, and then determine the upper and lower fences and see if there are any outliers. So the lower fence and the upper fence. The lower fence is the Q1 3.095 minus 1.5 times the interquartile range. And the upper fence is Q3 plus 1.5 times the interquartile range. So that's negative 0.3025, so there's no outlier on the bottom. On top, we get 8.7575. And if you look, there's no data values greater than that, so there are no outliers. All of the data falls between these two numbers, so therefore there are no outliers. Okay, so that's the idea of how this works. Now you can also do this, most of this using some technology. So let's try that to finish off this video. So we've actually already know how to find these things using class calc. So if I go to my data for this problem, so this problem is following data represents the hemoglobin in 20 randomly selected cats. So I go to prompt 3.4, number 2, because we did number 1 by hand in the end. And I copy my data into class calc. And then I'm going to change the name. And then we're going to do one var stats. So go to stat, go to advanced, choose one var stats, and then put in list A. And so now, from that, we've got all kinds of stuff we need. We've got X bar is 10.08. We've got S, which is 1.886, and that'll allow us, those two numbers will allow us to find the Z-score. But we also have the quartiles. Right, here's Q1, 9.15. The median is X median, so that's 9.95, and then Q3 is 11.1. Okay. So that gave us all the data we needed. Now we can go back and we can see if they're do some Z-score calculations and find out if find the Z-score for this cat named Blackie. So let's start with that. So to find the Z-score for 7.8, we use that formula. So that's the data point minus the mean over the standard deviation. So that's negative 1.209. Okay, so now we can interpret the interquartile range. So the IQR is 11.1 minus 9.15. So that's 1.95. And now we can use that along with the quartiles to see if there are any outliers. So we've got a lower fence is going to be 9.15 minus 1.5 times 1.95. And the upper fence is going to be 11.1 minus 1.5 times 1.95. Which is 6.225, and then the upper fence, this should be a plus, is 14.025. And so now we go up to our list, and we see, are there any data points that are not between those two numbers? And in fact, 5.7 is not between those numbers, so 5.7 is an outlier. Okay. So that is it for this video lecture. Next time, we'll talk about a visual representation of some of the stuff we talked about today. Make sure you're doing your homework and the quizzes. If you have any questions, feel free to email me or send me a message on Remind. And don't forget about either in-person classes or the discussion posts.